Hello everyone, and welcome to today's webinar titled MATLAB for Excel Users. My name is Addin, and I'm an application engineer at the MathWorks. My goal for today is to show you how you can use MATLAB to complement and possibly even replace Excel as your data analysis platform. Now, I would first off like to give you a sneak peek of what is our end goal for today. What do we mean by using MATLAB to complement your work in Excel? So I'm going to tab over to an Excel spreadsheet. This contains some data from a weather station in Davis, California. So you have some data for the date and some atmospheric conditions. We're going to worry a little later about what this data really means. What I'd like to focus your attention on now is this Run Analysis button we have over here. When I click on this, you'll see a couple of visualizations pop up. So what happened is when I click that button, it actually ran an analysis routine we developed in MATLAB to read the data from the spreadsheet, perform some computations, build a mathematical model, and make some predictions and produce some visualizations. And these are not static images. We can rotate them around, look at them in 3D. We can grab our data tip and look at particular data points. A lot of things we can do with these figure windows. We'll look at them in more detail a little later. This analysis routine also wrote out results into our Excel file. So this is one of the ways in which we can use MATLAB to complement our work in Excel. We can use it to develop analysis routines and then package them up in such a way that we can call it from inside of a spreadsheet, even if we don't have MATLAB installed at all. So it's a quick preview of where we're going today. To start off, I want to hop back to PowerPoint and start off talking about why Excel and MATLAB are going to look a bit different. Now, Excel is a spreadsheet, and spreadsheets are very good at showing you raw numbers. You're always looking at the numbers. But if we want to perform a computation, let's say we want to take the mean of this column of data, well, we first have to find an empty location in our spreadsheet. Click on it and go up to our equation editor, enter in equals average, and then the input to the function is the location in the spreadsheet without any data or name or any other meaning really attached to it. When we hit enter, it performs the computation, we see the result, but the math is hidden. It's there, but it's behind the scenes, and we're back to looking at just the raw numbers. MATLAB looks very different. We're not looking at the raw numbers here. Instead, our numbers are stored inside of variables, such as energy data. And we can look at the raw numbers if we want. But when it comes time to use them, such as taking the mean, we take the mean function, and then as an input, rather than giving a location, we give a named variable, energy data. The output, likewise, is not a location. It's a named variable, average day profile. So we can give much more meaning to the calculations we're performing, but we can always go back and look at the raw data if we're interested in it. However, regardless of if you're working in MATLAB or in Excel or any other platform really, we all follow the same basic process when we're performing data analysis. And we've laid that out here in a 3-step process to get everyone on common terms for today. So this starts out with what we like to call the access phase, where we're just trying to get our data from wherever it's living into our environment so we can start working on it. Today we're working with a particular file from Excel, but our data could be coming from anywhere. It could be images, could be videos, could be streaming in from other software like databases or off the web, or could be coming in live from hardware. Once we have our data in, then we enter what we call Explore and Discover. And ideally, this is where we want to be spending the majority of our time, analyzing our data, building up models, maybe developing an algorithm to analyze it, maybe even building a graphical application on top of it. But we can do all the analysis we want. It's not really useful to anyone until we share it with others. And that's our last step here. How can we take the work that we've done and share it? Either by automatically generating reports and documentation, which we'll see an example of, or generating specs for a design, or taking what we've built and deploying it to others so that they can use it without needing MATLAB. We'll see an example of this as well. However, if you're familiar with this kind of work, you may be noticing that we're missing something here. You will almost never go through this process in one shot. You may import your file and then realize that wasn't the right file. You need to import a new set of data. Or you may create a couple of different visualization routines. Some of them you like and want to keep, other ones you can get rid of. Or you may need to run through multiple iterations of your algorithm. So a key part we're going to talk about today is automation. How can we automate this entire process from start to finish, and also the individual tasks in between? So we'll be looking at MATLAB, how we can use it as a platform for data analysis. And the demonstration we're using to illustrate this is estimating solar radiation. So we'll be taking some raw data from Excel, bringing it into MATLAB, performing some processing on it, visualizing it, building a model out of it that we can make predictions, documenting it in a report, and then linking our work back to our Excel workbook. Now, I don't want you to worry too much about the theory behind estimating solar radiation. That's not the point of the presentation today. But I do want to give you some background on it and some motivation for why would we want to look at this kind of problem. Now, one of the motivations for this kind of analysis is for designing photovoltaic systems in areas such as developing countries where solar radiation measurements are not easily available. We want a simple and low-cost way to estimate solar radiation and thus estimate the power that can be generated from a photovoltaic cell. And we'll be doing that using this equation, which came from a technical article on this topic. There are many different equations we could use to estimate solar radiation. We picked this one because it meets our goal of using low-cost, readily available inputs. It takes as an input the relative humidity and the maximum change in temperature for the day. And the result is the solar ratio, which is the ratio between the radiation that hits the Earth's surface versus the amount that originally hit the atmosphere. So we have these actual measurements for each of these three, and our goal is to estimate the parameters A, B, C, and N to give us the best fit for our data. Because once we have those coefficients, we can then use them to make predictions on future conditions. So that's the end goal for today, is to build a model so we can make predictions on solar radiation. But for now, let's step back and go back to basics and take a look at MATLAB. So for those of you who haven't seen it, this is the MATLAB environment. We've got a couple of windows going on here along with some menus up top. We'll explain each of them as they become relevant. Now, this is the 2012B release of MATLAB. We have 2 releases a year, an A release in the spring and a B release in the fall. And the 2012B release was the largest release that we've had in a number of years. And the most obvious change comes up top in the menu system. We got rid of the traditional menu system and moved to a toolbar. And the real reason behind this was discoverability. We found that our developers had put a lot of time and effort over the years building different tools into MATLAB to help you with your work. But even many of our biggest power users didn't know about many of them because they were hidden behind menus. So we tried to bring them out to the front using the tool strip. And just to quickly point out a few of the more useful ones that people can find, just right here in the Home tab, we have a file comparison tool for comparing different versions of the same file and noting differences, an import tool for importing data into the MATLAB environment, the MATLAB code analyzer for analyzing your MATLAB code looking for inefficiencies and possible bugs, and the MATLAB profiler for running and timing your code and looking for places that may be slowing you down. So those are just 4 quick examples of what you can find right in the Home tab. Now, MATLAB at its core is a programming language. It's a language in which you can write and execute code. And one of the main ways of interacting with it is the command window over here on the right. So this is an interactive environment. We could use it sort of like a graphing calculator, executing simple commands. But we can also create variables. Maybe set a equal to 5 and then multiply it by 7. And you can see that we get the answer back immediately. Now, one of the things that makes MATLAB different from a lot of other languages is the way in which it understands data. MATLAB inherently understands all data as matrices or groups of numbers. So they could be 2D or 3D matrices, could be a row of numbers or a column of numbers, even a seemingly singular value, like a is equal to 5. MATLAB actually thinks of that as a 1-by-1 matrix of numbers. This is actually where MATLAB gets its name from. It stands for Matrix Laboratory. It's a fantastic environment for working with matrices. And just as a quick example, we can very easily create a matrix. Let's say we want to make a small 2-by-2. And then if we want to perform some operation on the different entries in this matrix, maybe we want to perform the sign on them, we can simply say, take the sign of C. And this will perform the sign on every entry inside of C and return the answer in the corresponding location in D. Now, one other thing I will point out while we're here is the workspace. You can think of this as MATLAB's memory space. This is where MATLAB displays all the different variables it has in memory and knows about, and that you can use when you're playing around in the command window. And we'll be coming back to this window a number of times today. But for now, we can go up and clear our commands, clear our workspace. Now we're back where we started. Now, if we think back to our data analysis workflow, that first step was access. We need to take our data from wherever it's living and get it into the MATLAB environment. So over on the left, we have a current folder browser. This is just the directory browser. It shows the location MATLAB is currently working in. And we see an Excel file in here, Davis Daily. And I'll open this outside of MATLAB. So this is the raw data that we got from the weather station in Davis. And you can see there's a lot more here than it was in that first spreadsheet. So we need to get this data into the MATLAB environment, but only the data that we're actually interested in. Now, anytime we want to do something in MATLAB, there's always multiple ways to go about it. We could write some code at the MATLAB command prompt to try and import the data, but our developers have already built a tool in the MATLAB to help us with that. We have this big import data button up here. This allows us to pick out our file, and it'll open it in the import tool. And the import tool is great for helping you import data into MATLAB, particularly when you want to perform some customizations on how it's going to be imported. In this particular case, we only want to import several columns as different variables into the MATLAB environment. We don't want the whole thing. So I can just pick out the date, the day of the year, the solar ratio, max and min air temperature, and scroll over and grab our relative humidity. We can also manually type in the range, set up a row to grab the variable names from. We could import it as column vectors or one big matrix, or maybe a cell array or a data set. We can also set up rules for how to handle certain things in Excel. For example, replacing unimportable cells that are either blank or contain text with a nan, or converting spreadsheet dates to a number, a serial number. And if we mouse over that inside of the import tool, we can see what number is it going to convert this date to. So now we can click on Import, and we can see back in our workspace, now we have those 6 columns of data inside of MATLAB as variables, and we can even look in the value and see what is the size of them. So we can see we have 3,653 data points. It's taken once per day, so we know we have about 10 years worth of data. So that was great. It was a very easy point-and-click environment. But let's say we shut down MATLAB and then start it back up and we want to get this data back in. Or maybe we have data from a different location besides Davis and we want to read that in. We don't want to have to go back through that same point-and-click customization every time. So one of the things we can do is inside of our import tool, below our big check mark, we have a couple of different options. Generate script or generate function. And I'll go ahead and generate function. So this generates what's called a MATLAB function file. And this function contains all the MATLAB code we need to recreate that import behavior with all its customization. You may have noticed we also got some new tabs up top. So these tabs on the left, Home, Plots, and Apps, these are global tabs that are always going to be there. But we also get contextual tabs that pop up when we need them. So when this file editor window opened up, we got the editor tab. So we can save this file. Let's call it import file. And now if I were to clear my workspace, now I can bring that data back in, just the data I want, using that customization by using the import file function, which, by the way, if we look in our current folder, popped up there when we saved it. And to save myself a few keystrokes, I'm just going to copy paste this down into the command window. And I'm going to tell it I want the import file function to run on Davis daily. And we see we get this same data back into the workspace. So now we found a way to not only bring our data in, but to automate that process, and we really didn't even need to know much about programming in MATLAB at all. But if we're interested in how we can do this process, we can scroll down through this function, and we can see both the code, and in green, we can see comments explaining what's going on. So as we scroll down, we can see, here it's importing the data, and we see several calls to a function XLSRead. That sounds interesting. So if we're curious as to what this is doing, we can right-click, go to Help on Selection, and it brings up MATLAB's documentation. So the documentation for MATLAB functions all have the same standard format. The function name, then a listing of syntax, different ways in which you can call and use the function, detailed descriptions, and then my favorite section, the examples. So if you're new to a MATLAB function, this is a great place to come to learn about how to use it and see some examples on how to get started. Okay, so now we've completed that first step, accessing our data. Now that we've got it into MATLAB, the first thing we might want to do is do a quick sanity check. Make sure that our data looks right, that we imported it the way that we wanted to. So for example, we could take our solar ratio, double-click on that. That'll open it up in the variable editor. So we can scroll through, look at the raw data. We can manually change it if we want. And we can do this for any variable in our workspace. We could also come in here and update the name. So this variable represents the day of the year. I could have updated that in the import tool, but I could also do that here by coming in and saying, you know what, let's rename that day of the year. Makes it a bit more obvious what that variable is doing. However, if we want to get a good sense for what's going on inside of our data, an easier way than just looking at the numbers is looking at a visualization. If you've used MATLAB at all in the past, I'm sure you've worked with visualizations. It's one of the most common usages of MATLAB. If we're not sure how to do that, we can go back to the help documentation, but there's an even easier way. If I want to see how the solar ratio is changing over time, I can select my date variable, then my solar ratio, and come up to this Plots tab and see that they're both selected here. And then I see that there's a bunch of different visualizations that are displayed. And if I expand this out, MATLAB has actually compiled all the different visualizations that MATLAB and the toolboxes I've installed have at their disposal that can accept the data I've selected as an input. So it's a great way to learn about new ways that MATLAB has for you to visualize your data. In this case, we'll just do a simple line plot, which just draws a straight line from one data point to the next. And this isn't a static image. We could zoom in and pan around if we like. But from this top-level view, it looks like there may be a certain cyclical behavior to it over time. But it's a little tough to tell because of what's down here on the x-axis. Now remember, when we imported the date, it automatically converted that date stamp into a serial number, which is much easier for performing calculations and using in plotting. However, it's a little tough to tell what that date is when you're looking at just the raw number. So what can we do to update our axes to make it a bit more readable? Well, we can go back to the help documentation, but there's another way we could search, which is using this little FX right next to the command prompt. This opens up what's called the function browser. This is sort of like the mini help for quickly searching just for functions. We could use the search bar, or we could search categorically. So we're working with graphics. We're trying to find out how to annotate this graph. And I want to know how to label my axes. So this displays all the different MATLAB functions for titles and labels. And we can see in here, here's a date tick function. date formatted tick labels. That sounds pretty good. So this gives us a condensed form of the documentation, and if we want more detail, we can click on More Help, and it'll open it up in the full help documentation so we can get all the detail we need. Now notice that when we clicked on that plot button, what actually happened is MATLAB figured out what command did it need to create that visualization, then printed it to the command window and executed it. So if we like that visualization, we don't have to go looking for what command do we need to recreate it. MATLAB has already given it to us. And now that we have it, we can use our dateTick function. And if I open the parentheses to start giving it inputs and just leave the cursor there, MATLAB will remind me what inputs is it expecting. So it's asking me, what axis do I want to put the ticks on? I want it on the x-axis. And then what format do I want the date to be in? So let's say 2 numbers for the month / 2 numbers for the year. And now we can see the x-axis is much more readable and makes it a bit clearer that it does look like there is a bit of a cyclical pattern going from year to year. Okay, so now we've done a quick sanity check. Data looks like what we were expecting. So now we may want to do some pre-processing before we start thinking about building up our model. One of the things we need to think about is this data was taken over a period of 10 years, and the instruments reading it may not have been up and working every single day for 10 straight years. So we need to find a way to search through the data that goes into our model, our relative humidity, max air temperature, min air, and solar ratio, to see if there are any locations where we're missing data, and then remove those lines from the data we're going to use to build our model. Now, the brute force way we can go about doing this is just looping through our data, looking at all 3,653 points one at a time, checking what their values are. But there's a much more elegant way we can do this inside of MATLAB, using something called logical indexing. And I'll demonstrate that with a simple example. So I've created a matrix here that we're going to use as a demonstration. Just as a bit of trivia, this is the magic square, which means that all rows, columns, and diagonals in the matrix add up to the same number. Now, if I want to grab a specific subset of data from this matrix, there are multiple ways I can do that in MATLAB. MATLAB stores its matrices row first and then column. So if I want this value of 6, I can tell MATLAB, go into matrix A and give me the third row, second column. And that returns a value of 6. We can also give it a range of numbers. So we can say go into the third row, and then if I just use the colon operator, that tells MATLAB, give me everything along that dimension, so it returns the third row, all columns. That's called subscripted indexing, and you are specifying the location within the matrix that contains the data you want. Logical indexing works a bit different. With logical indexing, if we want to, for example, have MATLAB give us all the values inside the matrix A that are greater than 20, we can simply say, give me from the matrix A all the values where A is greater than 20. And there we have it. This becomes even more useful when we want to modify these values. If I want to say go into the matrix A and take everywhere that is less than 5 and set that equal to 0, I can do that very simply with logical indexing. I don't need to search through the matrix for where that logical condition is true. I can do it in a single command. But if I'm interested in where those locations are, I can simply look at the logical condition itself. This returns a matrix of the same size as A that is binary. It's 1 wherever the logical condition was true, and it's 0 wherever it was false. So we're going to use this principle of logical indexing to search through these 4 variables for a logical condition. Then we're going to use the result of the logical condition to index back into them and return just the values that we want. So how can we do that? Well, in this particular case, We'll save the logical conditions to a variable. We'll call it TF. And we're going to make use of a function called isNan. What isNan does is it looks at the input, this matrix for relative humidity, and it checks if the entries are nan, which it stands for not a number. And remember, when we were importing our data, we told it that any unimportable cell, anything that's blank or maybe has text, replace that with a nan. So this will find all those locations and return a vector of zeros and ones, a 1 where it was a nan, and a 0 where it did not find a nan. So I can ask, is it a nan in the relative humidity? Or is nan in air temp, max air temp? Or is nan in min air temp? Or is nan in the solar ratio? So I'm combining the logical condition for all 4 of these. But isNan returns a 1 if it was a nan, not a number, and 0 if it was not. I want the reverse. I want it to be true when the data was valid. So we're going to use the tilde operator to flip 1s to 0s and 0s to 1. And notice that we can do this in just a single command. We can operate on these matrices in one line of code. And now we have our TF variable down in our workspace, and we can see it's the same size. So now we just need to index into our other variables. So we can say, I want you to override our old value for average relative humidity, create a new one that is equal to the original value wherever TF is true. And do the same thing for date and day of year. And notice as we do this that we can see down in the workspace it's changing size. So we're actually removing several dozen data points that correspond to when we were missing some data. So we need to finish this for our 6 variables. Max air temp is equal to max air temp of TF. Min air temp is equal to min air temp of TF. And the solar ratio is equal to the solar ratio of TF. Okay, so now we're done with some pre-processing to search through our data, find the locations of bad data points, and get them out of there. And we were able to do this pretty quickly with just a few lines of code in MATLAB. So now that we've processed our data, we've gotten rid of the bad data points, now we may want to look at these in a little more detail. And maybe we want to look at our solar ratio again, and look at how it's changing over time. We saw initially that looked like there may be some cyclical nature. So we may want to look at how it's changing by day of the year, or how it's changing per year. But we don't have just the year right now. We have a serial date number. So we need to find a way to take this serial date number and get out what was the year at every point. So we can come back to our function browser and just type in date. And so we see a list of functions related to date. First one that pops up shows us what the current date is. Next one, date num, creates the serial date number we already have. Here we go, date vec. This converts our date number into a vector of its components. So the year, month, day, hour, minute, and second. So we want the year, but we're really not interested in any of the other variables. So rather than create unwanted variables and clutter up our workspace, we can use the tilde operator to tell MATLAB, hey, I'm not interested in this variable, don't bother creating it. And there we go, now we have a variable for year. So now we can come into our workspace, similar to how we did earlier, select day of the year, and solar ratio. Come up to plots, and now we notice that since we have 3 variables selected now, the available plots have changed. So we may want to start with a scatter plot, which will put a dot at each data point in the 3D axes. But by default, this is a little hard to read. It looks like just sort of a big blob. It's tough to tell if a particular data point, let's say this one, is high on the z-axis or if it's low on the z-axis and just pretty far back in terms of x and y. So let's customize this to make it a bit more readable. Now again, multiple ways we could do that. We could write out some MATLAB code to do it, but I'm going to show you my favorite way, which is using this button up here to open up the plot tools. And the plot tools is a palette environment that allows us to interactively customize our visualization. So we can come and select our data, pick out the color that we want, and let's say we want to color our data points according to their z value, which is the solar ratio. Refresh our data, and there we go. We can change the marker. Let's make it a small dot so that this becomes less of a big blob of points. We can also select our axes and label them. So we can say this is day of the week. Here's our year. And this is our solar ratio. We can also do some more complicated things. If we wanted to create subplots, which are multiple axes inside the same figure, we can just draw out what do we want the orientation of them to be. We could also add in annotations. Let's say draw a text arrow. So we have an arrow pointing to a certain location with some text explaining what's going on there. We can do a lot of customizations from this plot tools, but eventually we'll be happy with what we have. Let's say this is good enough for today. We can hide our plot tools and get just our figure back. So we went through and we customized it and we got a nice figure that we're happy with. But if I were to click this X button up here, we would lose all that customization, and if we wanted to recreate this, we would have to go back through that point-and-click interface. So keeping with the theme of automation, to save this, we can go up to the File menu inside of our figure window and go to Generate Code. And this will generate a MATLAB function that captures that behavior, very similar to what the import tool did. So now that we have this file, we can save it. Let's call it Create Figure. And if we close all our figure windows, we can now call Create Figure, give it the day of the year, the solar ratio, and then it has this fourth input, S. This is the size of the marker. I'm going to leave that blank by giving an empty square bracket. This tells MATLAB to just go use the default. And then we need to tell it what variable do we want to use for coloring, and that's just the solar ratio, the same as the z value. And then we get this customization back up. So this is a great way to easily customize your visualizations, get them the way that you want, generate some code, and then that captures all the customizations so you can reapply it, revisualize new data using those custom settings. It is not tied to the data that you used to create it in any way. This also can be a great learning tool. Since MATLAB is giving us the code that we need to create this figure, if we want to know how to programmatically create a certain custom visualization, if we're not sure how, we could go to the help documentation. Perfectly valid way to do it. Another way we could do it is create a MATLAB figure, open up the plot tools, do the customization interactively, then generate code, and MATLAB will give us the code that we need to go in and create that custom visualization programmatically. Okay, so now we've gone through, we've imported our data, automated that. We did a quick sanity check, did some pre-processing, visualized our data, customized it, automated it. Now it's time to start thinking about creating that model. Now, when we create our model, ideally, we would like to have some data to test it against. So what we're going to do is we're going to draw out a certain subset of the data. So I'm going to create a variable here, IDX, that's going to be equal to when year is not equal to 2006. And we're going to use this logical indexing to pull out our data from the years that are not 2006. We're going to use that data to build our model, and then to test the accuracy of our model, we're going to use it to predict conditions in the year 2006 and compare that to what the actual data was. Now we do need to create one more variable, which is the change in daily temperature, del T. And this is just the max air temp minus the min air temp. And now we can grab out just the subset not associated with the year 2006. So we can call this my del T is equal to del T of 2006. And then we need the other two variables associated with our model, which is our relative humidity. Oh, and I had a little typo up above. Need to use the actual variable we created. What I did there, just grab the 2006 index inside of del T. And then we also need to grab our solar ratio. Okay, and when we check the size below, we can see that the three variables we just created are a few hundred points short of their original size. So now we've got just the data that needs to go into our model. We've grabbed just the subset that was a valid data point and is not associated with the year 2006. So now we're ready to go ahead and build our model. And in order to do that, I'm going to go over to our Apps tab. And you can see the Apps tab looks a bit similar to the Plots tab, shows us a number of different apps up here. And when I expand these down, you can see all the different apps that I have available. And these apps are great because they provide a graphical interface that allows us to explore the functionality of MATLAB and its toolboxes and apply it to our work before we need to worry about what kind of functions do we need to call and what kind of syntax do we need to use. So in this case, I'm going to open up the curve fitting app. This comes from the curve fitting toolbox, and the curve fitting toolbox is great for fitting equations to data that is 2D or 3D. So equations of the form y is equal to f of x and z is equal to f of x and y. So we can set our x data to our change in temperature. That's going to be our first independent variable. Our second one, our y data, is going to be our relative humidity. And the dependent variable is our solar ratio. Now by default, MATLAB tries to fit a linear interpolant to our data. A linear interpolant is a piecewise function where we have a large number of flat planes, like pieces of paper, that MATLAB fits together edgewise so that it can try to fit it through every data point perfectly. Now, interpolants aren't really useful to us here because since they fit through every data point, they fit to the noise of our system, and we're more interested in capturing the general behavior. So we could try maybe a polynomial fit. With degrees of 1 in x and y, it comes out to just a plane, as if we were trying to take a sheet of paper to capture the behavior of this entire set of data. On the left, we can see the results, which shows the form of the equation, the computed coefficients with confidence intervals, and a goodness of fit measure. However, we already know the form of the equation that we want to fit. So we can enter in our own custom equation. And for us, it's going to be a times 1 plus b times y, which is our relative humidity, times 1 minus the exponential of negative c times x to the n. And there we go. So now we fit our custom equation to our data, and we can see on the left the results, the form of it, and the computed coefficients and the goodness of fit measure. And there's some other things we could play around with in our curve fitting tool, but this looks pretty good for our purposes today. So let's say we're happy with this fit. Now what we want to do is we want to get something out of this that will let us make predictions, and also, again, automate this process so that if we get a new set of data, we can refit this custom equation to that new set of data without needing to go back through the app. So just like we've done before, we can go up to File, inside of our curve fitting tool, Generate Code. And MATLAB will give us the code that we need. So we can come down and close our curve fitting tool. Let's go ahead and close the import tool as well. We don't really need that. So now we can save this function, call it create fit. Now when I call create fit, I need to enter in my del T, my relative humidity, and my solar ratio. And we can see that it recreates that same fit, refits it, recalculates the parameters to fit this set of data, gives us our visualization back, but this function also has an output, which we've saved here as model. So model contains the equation as well as the computed parameters, and we can actually then use this to make predictions. If the change in temperature is 20 degrees with 90% humidity, it makes a prediction that the solar ratio will be 0.498. However, we know there's a lot of variability in this data. Under these conditions, chances are it's not going to be exactly a solar ratio of 0.498. So we'd like to know how confident are we in this estimate. So the curve fitting toolbox has a function called predInt, short for prediction interval, that can accept our model. And then what are the inputs to it? 20 and 90. And it returns our 95% confidence interval to tell us how confident are we in these predictions. So we created this model using the data from outside the year 2006. Remember, now we want to see how well did it perform versus the actual data from the year 2006. So remember, this is MATLAB. This is the matrix laboratory. We don't need to work with just scalar values here. We can give it an entire matrix. So I can say the matrix for my estimated radiation is equal to model. And I want to give it the change in temperature for the year 2006. So that would be del T, not IDX. So IDX shows where the year is not 2006. So if we negate that, it will tell us where it is the year 2006. So we need to give it del T, and also the relative humidity for the year 2006. And so that just ran each of those conditions through our predictive model and gave us the results. Now we can look at a comparison between what was the actual solar ratio then and our estimated ratio. And there's a number of ways we could look at it. Today we'll use a stem plot. So for a stem plot, we need to give it the day of the year for our X data. And again, we need to tell this that this is only the subset associated with the year 2006. Then our Y data is going to be our actual measured ratio for the year 2006 minus our estimate. And then I'm going to give it an optional parameter here, just customizing how it's going to display things. And we can see our stem visualization showing the error between our actual solar ratio minus the estimate that our model created. So now we can do a visual inspection of this and get a better sense for how accurately was our model able to predict the conditions in the year 2006. Okay, so that's great. Now we're pretty much finished with our problem. We completed that second step, explore and discover. Now we want to take the results that we just figured out and we want to share it with others. So how can we do that? Well, I'm going to bring up a window that's been hidden so far called the command history. And all the command history is a collection of commands that have been executed at the command prompt Goes back quite a while. Mine goes all the way back to this past September. So it's great when you have those moments of, well, how in the world did I do what I did yesterday? You can go back to your command history and check. But one of the other things it allows us to do is to look back through everything that we did interactively at the command history and save just the parts that we want to keep. So we can come back and save import file. Then we can save this customization that we're doing here, or excuse me, the logical indexing. We can grab just our custom figure. And grab what we need to create our model, and maybe make a prediction, and grab our stem plot. So we're grabbing most of what we did today, but we can pick and choose what we want to keep. Then we can right-click and click on Generate Script. And this will take everything in the command history and copy it over to a MATLAB file. So now that we have this file, we can save it. Let's call it my script. Oh, but one important note, this only captures what we did at the command window. If you'll remember, I changed the name of this Julian vector to day of the year to give it a bit better meaning. So if I want that to be true here and to be usable further down, I need to come back and make a small modification. But now I can save this, and we can go and clear our commands, clear our workspace. As if we had shut down MATLAB, we come back the next day. And now we can take this my script, we can come to our editor tab, click on run, or we can simply enter my script in the command prompt. And it will run through every command as if we had executed it one by one at the command prompt, and get back all of our information. So now we're right back where we were. Now we can hand this off to somebody else, but if we gave them just this code and they weren't familiar with our work, it may not be too obvious what it is that we're trying to do. So it'd be a great way if we could explain inside of our file what we're doing. And we can do that using MATLAB comments. So we can comment things in MATLAB using the percent marker. You can see that this turns the text green, which just means that it's not something that's going to be executed. It's only there for explanation purposes. There's another kind of commenting, which is the double percent marker. This creates what's called sections inside of our MATLAB code. And I'm going to add one more down here for modeling. And for completeness, we'll add one more on top. This is for import. Now these cell sections have a couple of advantages to them. One is they're just more visually distinct when you click through them, but it also allows us to run our file piece by piece. So now that I have these cell sections, I can use these commands on the right of our editor tab to run in advance. So to run the current cell, and just that one in advance to the next. So now we just imported our data, but we haven't done the pre-processing yet. Now when we click again, we do the pre-processing, but we haven't done the modeling. We can even go back and run just the pre-processing again without running the previous sections. So it's great for debugging because we can run the same section over and over again without running the preceding ones because we know that those work. And of course we can come down here and run modeling section and get back our stem visualization. Now the other big benefit of using code sections comes when we want to share it as a report. So we have this Publish tab up here we haven't looked at yet. Publish contains some options for helping us annotate our MATLAB file so that it publishes in the way that we want. For now, I'm just going to click on the Publish button. And what Publish does is it runs your MATLAB script and captures all the outputs and compiles it into a report. And you can see that the section titles become the titles of the different sections in the report. Regular comments populate the text, captures our commands, visualizations, and any output to the command window. So it's a very quick and easy way to capture what you've done in your MATLAB file into an easily readable report. So I think you can see how we can start building up these reports and commenting them to get them to publish in a certain way. as a brief example, I'm going to bring up a larger script that runs through the same problem in basically the same way. We've just done a better job of commenting it so you can see some of the things that we can do when we publish. So you can see here we have an introductory section before our table of contents. We're including things like URL links. We can jump down to a certain section. So we can jump to a section in our report. We can include things like well-formatted algebraic equations by including LaTeX commands inside of our MATLAB comments. We can also do other things like bulleted and numbered lists, bolding and italics. There's a lot of things we can do to customize the way we want this report to be generated. There's only one more option I'm going to point out while we're here, which is inside of the publishing options, and that is the output file format. By default, it's the HTML, but it can also publish directly to XML, LaTeX, Word doc, PowerPoint, or PDF. All right, and that's pretty much it for solving it for that one particular file. But what if we have multiple files that we want to perform this analysis on? I actually have that today. I have a subfolder, Solar Data, that contains 12 different files with the same data from different locations. Now, since we have limited time today, we're not going to work through from scratch how to work up that automation routine, but we'll take a quick look at it. The first thing we need to do is convert our script to a function. And this is a very easy process. We can simply add a line at the top saying function. Outputs of the function is equal to the function name and then the inputs. And if we scroll through our function, we can see we're doing all the same things. We're importing our data. We're doing our logical indexing to get rid of the bad data points. Indexing for outside the year 2006. Creating our fit. Performing our predictions. So we're doing basically the same problem, and we can even test this very quickly. And say model is equal to solar analysis function of Davis daily. And it runs through the same process. Gives us the same output. Only now we've packaged it as a function. And the great thing about this function is all we need to do is give it the file name, and it will run through all of our work and give us back out the model that we want to use to predict. So then how can we take this and start automatically running it on a large number of files? Well, we can use commands like full file and the directory command to search through a subfolder like solar data and grab all the different file names that end with daily.xlsx. We can then, inside of a loop, display that name, build the full path, run it through our function, and store the coefficients. So here we can see it's running for Bennett Valley, and now for Bishop, and for Brentwood, and for Camino. So you can see it's pretty easy to take this script that we had, convert it into a function, and then grab the files that we're interested in, and just loop through those files and apply this function to all of them. And let's see here, I believe we have one more to go. And there we go. So we ran through all 12 of those files and automatically ran our solar analysis function on it and also saved out the coefficients. And now, at last, we're using XLSWrite, the opposite of XLSRead, to write this data back out to Excel. To solar fit results. And we can see we wrote out in the first column, what is the name of the file, and then the 4 coefficients associated with it. So we went from data in Excel into MATLAB, ran it through our analysis for all 12 of those files, and then wrote that data back out to Excel. Okay, so now we're going to step back to our slides for just a moment and wrap that up. So for the main portion of our demo, we went through reading in files from Excel. We did a bit of analysis and modeling, didn't really get into algorithm development or application deployment today. And then we saw some reporting. And very quickly at the end, we're going to see an example of deployment. How can we take this and link it into Excel? So first off, what are the different ways we can share our applications? The ideal situation is we have MATLAB and they have MATLAB, and we can just give them our MATLAB code. However, if they don't have MATLAB, we can use something called the MATLAB compiler to build our applications into EXEs and DLLs that they can run without MATLAB. We can also use our builder products to create Excel add-ins and also components for Java, COM, and .NET. So let's take a quick step back to MATLAB and see how can we, let me clean up those figure windows, how can we create that Excel add-in component? Well, I'm going to go back to my Apps tab and open up the app for the MATLAB compiler we just mentioned. And I'm going to open up a project for an Excel add-in. And all I need to do is drag and drop the function I want to use in Excel from my current folder into the compiler app. And then I can hit build, and MATLAB will take care of the rest. It'll figure out a dependency analysis, what functions does this one call, and it'll build it into all the files that I need to use it as an Excel add-in. Now, it's a pretty simple and straightforward process to build this and then add it into Excel, but it does take a couple of minutes, and we're under some time constraints today. So we're going to skip that for now, but the end result is inside of your Excel worksheet, you can create something, for example, a button, where when you click on it, it will run a macro from that component that we created, and it will run that function exactly the same way that it ran in MATLAB. And we can have it output to Excel, we can have it create MATLAB figure windows, and we can then take this and send it to somebody else who doesn't even have MATLAB. So how does that compiler process work? Well, to start, simply build your application in MATLAB as you normally would. It could be graphical, or it could simply be a collection of functions. Then you need to pass it through the MATLAB compiler, or if you're going to Excel, the Builder EX as well. And out the other end come the components that you need. One of the great things about the Builder EX is you don't need to write any VBA code. In fact, you don't need to write any code outside of MATLAB at all in order to use it. You can then give it to anyone else that you want. But these components are running MATLAB code under the hood. So in order for them to run, they need access to MATLAB's runtime libraries. This is where something called the MATLAB compiler runtime comes in. This is MATLAB's runtime libraries compiled into a distributable form. You can either package this up with your components and send it to somebody, or they can download this directly from the MathWorks website. And these components, as well as the compiler runtime, are free to distribute. There are no licensing restrictions, there are no royalties. You can give it to as many people as you like, you can sell it, you can even turn around and make a profit off of it. Okay, so when it comes to MATLAB interacting with Excel, there are a couple basic ways. If you just want to pass data back and forth, you only need base MATLAB. If you want to access MATLAB from Excel and pass data back and forth live, you can use something called the spreadsheet link EX, which we didn't see today, but this does require an open, active running version of MATLAB. If you have the MATLAB compiler in Builder EX, then you can build MATLAB into an Excel add-in and give it to somebody who doesn't even have MATLAB at all for them to use. Now, if you're working in a specific domain, say signal processing, computational finance, image processing, MATLAB also has a number of toolboxes for these areas. These toolboxes contain many different functions and visualizations and GUIs that contain solutions for these areas so that you can focus just on the work that's interesting and not need to reinvent everything in the MATLAB environment. So there are many different benefits to using MATLAB. Some of the ones I hope you saw today. is there are thousands of engineering, science, and math functions built into MATLAB ready for you to use. There are extensive plotting capabilities. It's very easy to customize them. It's also very easy to find ways to automate a lot of your analysis, and it integrates very well with Excel as well as other environments. So if you're interested in more information, I strongly encourage you to check out our website, mathworks.com, and look at the different product pages. So this is the product page for just base MATLAB. And you can see on the left, it lists sections for videos and examples and webinars, and this is a great place to find out more information about a particular product. So that about wraps it up for today. Thank you for tuning in, everyone.